problem easy sums requires calculating the sum of reminders for multiple test cases. Input T number of cases for each test case, two integers n and m. Steps for each I from 1 to n, calculate the remainder when I is divided by m and sum them. For example, n equal to 10, m equal to 5. The remainders are 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, and their sum is 20. Output print the total sum for each test case on a new line. This problem highlights the need for efficiency as n and m can be as large as 1 billion. Thank you.
So I'll be discussing the problem 2, pairwise sum and divide. At first, we are defining an array and checking if the constraints are met. And here we are setting a variable where the position of the element is defined. And we are doing a calculation for the numerator and the denominator. And they are divided by each other. And the value of that is added to the list. And then it is repeated until the position is equal to the length of the array. Then as you can see, the pair of last value and first value isn't there. So we are doing this calculation for that. And at last, we are getting the sum of the whole list and floating it. So in my case, it's 3/2, and it has been floated to 1. So that's how we solve the problem 2.
This calculation, we are going to solve a big sum. If the big sum is s, s can be defined as 1 into power n plus 2 into power n until k into power n. Since n and k can be bigger, the resultant also can be bigger. For that, we are going to use modular arithmetic. For example, 175 mod 100 is taken as 75. The literal definition is to take the division of the number from 100. To take the I into power n mod 100, we are going to use modular exponential. Using this, we are going to break down the power calculation into smaller steps and to make the remainder smaller. When calculating I into power n mod 100, we are going to take the remainders of each numbers and try to get the sum of it. And then we are going to get the sum mod 100 and going to take the last two digits of the number.
Let's break down the problem of scalar products step by step. Imagine we have two vectors A and B, each with the same number of elements. The goal is to compute the scalar product, which involves multiplying corresponding elements from the two vectors and then adding up the results. Here's an example. Suppose A is equal to 2, 4, 6, 8 and B is equal to 1, 3, 5, 7. First, we multiply the first elements. 2 by 1 is equal to 2, 4 by 3 is equal to 12, 6 by 5 is equal to 30, 8 by 7 is equal to 56. The results are collected in a set P, which is 2, 12, 30 and 56. Adding these together gives us 100, which is the scalar product of A and B.
Today I am going to solve the problem number 5, sum in the Kane series, and I am going to use the Fold-Hebers method to solve this question. As a step 1, we need to create a Pascal triangle up to k plus 1. This gives combination need for the formula. Step 2, we need to use this formula to understand the problem. Then step 3, step-by-step calculation. Start with S n0 equal to n, sum of first. Then calculate each higher up to k. Solve recursively using lower powers. Use modular arithmetic rules for calculations. Then step 4, modular arithmetic. Modular arithmetic, perform operations modular 10 to 9 plus 7 and use the modular inverse for division. Example, for n equal to 5, k equal to 2, then S50 is 5, S51 is 15, S52 is 55. This demonstrates how to recursive approach work in solving the series. So as a conclusion, by following these steps, we can efficiently calculate the Kane series for large value for n and k under modular constraints. Thank you.
A series is simply the sum of the term of sequence which can be finite or infinite. Think of famous examples like Fibonacci series or simple arithmetic and geometric series. For instance, 2 plus 4 plus 6 plus 8 is an arithmetic series with a common difference of 2. Step 1. Understand the series type. Identify whether the series is arithmetic, geometric, or Fibonacci. Series 2, 4, 6, 8. Step 2. Write down known terms. List the term of the series given in the problem. Example 1, 3, 6, 10. A1 equal 1, A2 equal 3, A3 equal 6, A4 equal 10. Step 3. Identify patterns. Check for differences or ratios between considered terms. Example differences 1, 3, 6, 10 is, is to 2, 3, 4. The difference increase by 1 each time. Step 4. Check for arithmetic series. If there is constant difference, use the formula. The formula is an equals a1 plus n minus 1 into d. Example 2, 4, 2, 4, 6, 8. The difference is 2. Step 5. Check for geometric series. If there is a constant ratio, use the formula. Example, the equation is a n equals a1 minus r into the power n minus 1. Example, for 2, 6, 18, 54, the ratio is 3. Step 6. Summation formulas. For the sum of the series, apply the arithmetic formula. First, arithmetic sum. The equation is Sn equals n by 2 into a1 plus an. The geometric sum. The geometric equation is Sn equals a1 into 1 minus r e to the power n divided 1 minus r if r less than 1. Thank you.
In this problem, n children sit in a circle, each starting with a number. Over m rounds, each child updates their number based on the sum of their immediate neighbors. The formula for updating child i's number is a sub I equals to a sub I minus 1 plus a sub I plus a sub I plus 1 with circular indexing. After each round, results are calculated modulo a to the power of 9 plus 7 to prevent overflow. The output shows the updated numbers for each child starting from different positions. The problem involves circular indexing and modular arithmetic.
Today, we will learn how to count distinct equations in the form of x plus y equals z. Here, x and y are integers ranging from 1 to n. The goal is to find how many unique values of z we can get. Let's take an example where n equals 4. The possible pairs for x and y are 1, 1 to 4, 4 as given here. Now we calculate z for each pair like stated here. Finally, we get unique values for z. In this case, we get two numbers from 2 to 8. This method can be applied for any n by listing all pairs, calculating z, and counting unique values.
So I'm going to explain about XOR love. XOR compares two binary numbers bit by bit. It outputs 1 if the bits are different and 0 if they are the same. For example, 2 XOR 3 in binary is 1 0 XOR 1 1 equals to 0 1, which equals 1. For this problem, you are given a number n to create a list A from n down to 1. Query is given three numbers k and a range p and r. First, select the sublist of A from p to r. For this range, find all unique pairs ij where I equals j. Next, calculate ai XOR aj for each pair and then XOR the result with k. Add all these results together to get the answer for the query. Repeat this process for all queries. For example, if k equals 1 and the range is 1, 2, 3, you will calculate pairs like 1 and 2 and 1 and 3 and the sum the results. That is simple steps to solve XOR.
Okay, so this is basically how we enter the data, and these are the conditions we have to follow. So here we have entered the values for m, the values for the a values and the b values. Functions px and qx are defined like this. We basically substitute m and the values for a and b in order to get the in order to determine the functions as seen here. Now, then we found a rational function Pn over Qn, which would be 1 over n times n plus 1, which we then broke into partial fractions. Then we try to find the series. To do so, we substituted n equals 1 until n equals capital N like this. And you can see that these terms would cancel each other out. So we are left with 1 minus 1 over n plus 1 as seen here. Then we try to find this infinite series. So we used limits n goes to infinity for this series. And then we got the answer 1. and they say if the sum of the infinite series is an irreducible fraction, which in this case it's not, this is how the output should be like. So this is, they have explained how the output should be, but in this case it is not an irreducible fraction, so the answer is just this, which is 1.